Welcome to LED Luminaires. Light Planes, Part 1, An Introduction to Light Energy, presented by the PLC Professor. This is the first presentation in a series, the goal of which is to assist you in building a light plane. Before we begin, I would like to emphasize several points. First, depending upon your background, this presentation at some point may go into more detail than you want. Some information may go over your head, or the entire presentation may bore you to tears. My presentations are normally tailored to the novice with enough technical detail to entertain the viewer who already has some technical background. In some cases, I will use representations of information and not actual warranties of information, meaning that I may take technical license on occasion to make my point. I am only concerned for those who find some of the info too technical, and if this is you, hang in there as we go through this information. Hang in there, don't give up, don't strain your brain to comprehend and retain everything in these presentations. I will swing back and forth between the technical and the practical, but eventually I will always get to the practical. It is not necessary for you to retain everything that we're going to go through, but I at least want to give you a chance to learn some of the basics of the behavior of light and light energy nonetheless before we start. A luminaire is an electrical device used to create artificial light by use of an electric device. They say artificial light because it is not light produced by energy from the sun. Nonetheless, a photon of light, a bundle of light, a piece of light is light regardless of the source. The light that comes from the sun, its individual photons, its individual pieces or components are totally undiscernible from any other source of light. Light is light. All light fixtures have a fixture body and a light socket to hold the lamp and allow for its replacement. Now, the luminaires that we're going to get into don't have a socket, and they do not necessarily lend themselves to easy replacement because we're going to be using LEDs. Fixtures may also have a switch to control the light. Fixtures require an electrical connection to a power source. Now, permanent lighting may be directly wired and turned on and off with a wall switch. And movable lamps usually have a plug. Your luminaires can be built either permanently wired in the area that you're going to use them, or they can be portable. They can be hung on the wall and you simply unplug them from a socket. Disconnect the power cord is to make it easy to transport. Take the thing off the wall and put it someplace else. Light fixtures may also have other features such as reflectors for directing the light, an aperture with or without a lens, an outer shell or housing for the lamp alignment and protection, and a power supply. Now, most of you are familiar with the electric lamps that sit on your tables. They have a plug that goes into the outlet. The power supply is actually the power company many miles away. You have a switch to turn it on and off. So we're going to do something a little bit more complicated than that. Now, for lack of a better term, I have coined the term light plane. And in this case, a light plane is a subset of luminaires. Luminaires includes all light fixtures, and light planes is just one in the subset of luminaires. The term plane, P-L-A-N-E, in mathematics, a plane is a flat, two-dimensional surface. So when we say plane in context of this lecture, we're talking about a flat surface. It does not have to be rectilinear. It doesn't have to be a rectangle or a square or a trapezoid. It's just flat. It could be a circle. It could be an ellipse. Now what we're going to build will be rectangles and squares because that's much simpler to build with materials easily obtained at your local lumber supply place. So in mathematics, a plane is a flat two-dimensional surface. When you first saw light plane, you may have thought airplane, light plane, water plane, plane. Airplane is really one word. Aeroplane originally referred to just the wing, as it is a plane moving through the air. In other words, it's a flat surface moving through the air, therefore it was an airplane. It planed the air. Light plane is two words to be thought of as a plane of light or a surface of light. So when we say light plane, building a light plane, creating a light plane, we're designing a luminaire that to the human eye appears as a flat surface of light. This, the first presentation, is a conceptual introduction to the behavior of light. A comprehension of this subject will allow you to deviate from building a pre-designed light fixture, in other words, following what we did step by step and coming up with the exact same thing we came up with. It will allow you to deviate from a design that you see step by step to imagining your own designs based on being able to visualize the results of a design before you actually build it. In other words, if you learn more about light, the behavior of light and light energy, and you watch, the rest of these videos, this is just the first one, you should be able to sit and contemplate the behavior of light. And if you mounted this light sources in a particular manner within your fixture or your structure, you can imagine the results before you actually build it. Now, most of the time, after you build it, it doesn't come out exactly the way you pictured it, but it should be close enough that you can make some adjustments and end up with the result that you want. Always remember, it is about perception and not reality. It is about how something is perceived and not the inner workings that create the perception. You need to think about that for a minute. As long as you create the perception of a lit surface, a surface of light, to the human brain, it's just a surface of light. Regardless of how you created it, light from the front, light from the back, or the surface being a light itself, it is still just a light plane. Here we have a graphical representation of a plane. A plane is a flat two-dimensional surface. We added a little extra graphic to it to look like it's a box, the front of which is light. So a light is an object from which light comes forth. So imagine a flat surface, a plane, as perceived by the human eye. If you can see the entire surface, then it is a light. Not a source of light, that is the energy thereof, but a light. For centuries, windows were referred to as lights. Architects quite often refer to windows as lights because they allow the entry of light. We show here a surface as the front surface of a shallow box to clarify that it is tilted roughly at 45 degrees and facing to your left at an angle to your view. So you're standing to one side looking down on a box that has a lit surface. Now let's turn out all of the lights in the space to put the plane in total darkness. Okay, here's our same, if you want to call it, shallow box with a lighted front. If all the lights have been extinguished in the room, the shallow box would not be visible. So now we have just the light plane. The reason that we showed the shallow box is because at this point, if you began with just this image, you wouldn't know whether you were looking at the bottom of some strange shape, you were looking at a trapezoid, you wouldn't know really what you were looking at. So first we had to build the image, and then we turned the lights out so you have a spatial perception of this surface. Now, as you stare at this object, imagine where the light source is located. Now you see this lit plane, this light plane, but you really don't know what the source of light is, where the light is coming from. You just see a rectangle in front of you that is lit, and it does have a tone, a color, a hue. It looks magenta. Now, as you stare at this object, since you don't know, you cannot determine from what you see if the surface is the light source or the light source is behind the surface, shining through the surface, or the light source is in front of the surface, which is to say that there would be a spotlight in the upper left out of your view that is illuminating, we'll say, a white square with magenta light. Now, in order to have that be a spotlight, everything in the room would have to be literally, totally flat black and absorb all light, so you wouldn't see any light reflected off of any other object in the room. Now, you probably can't see it, but I left a really slight edge around the border of this rectangle just to remind you that there is an object there. So you just see a lighted surface, but you can imagine it is a light source, or, in other words, when I say a light source, I mean like a flat screen monitor or TV. It's a surface that puts off light. So you can imagine that it could be a light source itself, or an aperture through which light is passing through. So if there was a light source behind it, as the light passes through, depending on what the surface is made out of, the light passing through would be scattered in all directions from the surface, and you see the surface. Or again, it could be reflecting light from another light source that is above. You really can't tell this by looking at this surface. That's why we said it's the perception that matters, not the working. So we don't care if the surface is a light source, if the light's coming from behind, it's coming through an aperture that has a diffuser to scatter the light, or the light is coming from the front of the rectangle and reflecting off of the surface to give you a lit plane. To your eye, what is the difference between light reflected off of a white surface or light passing through the surface? There is a difference in reality, but not in perception. Just in case it has crossed your mind, light passing through the aperture, meaning if the light was behind the rectangle and it was passing through an opening, an aperture, light passing through the aperture would appear different for a translucent aperture versus a transparent aperture. In other words, if that surface was a film or plastic that was translucent, meaning you can't see an image through it, but light can pass through it, versus if it was glass, clear glass. Okay, this illustration is for a translucent aperture, not a transparent one. If this aperture were of the transparent type, and the atmosphere in the room was totally free of dust, in other words, there are no particles in the air for the light to hit, you would not see any light at all from your current viewing angle. Now, we will demonstrate this later. So this square, or this rectangle that you're looking at right now, if this were to be a piece of clear glass and you had a light source behind it, you would not be able to see any light at all. You would have to be standing directly on the opposite side of that piece of glass to see the light that was behind it. And we will demonstrate this later. There is really no difference in the light reflected off of the surface, passing through an aperture, or radiating from the surface as a light source itself. A photon of a certain wavelength is a photon of a certain wavelength. Earlier, I said that you couldn't discern the photons from the sun from photons coming from another light source. I meant a particular wavelength. So if you have a photon of red coming from what they call artificial light or from the sun, they're identical. Now the sun has a spectrum that, if analyzed very carefully, in other words, all the different wavelengths, all the different photons, you could identify that combination came from the sun. But when you're talking about an individual color, an individual wavelength or photon, regardless of how it was created, once it leaves the source, they have the same property as any other photon of that color and wavelength and strength. Okay, light energy travels as photons. That is the term we use to describe a piece or a fragment of light. When your eye perceives magenta, it is receiving photons through your iris. That's the clear lens on the front of your eye, and the opening that expands and contracts depending on light level. These photons pass through your iris and impinge on the back of your eye, which is the retina. Where the energy started, how many different conversions it passed through to reach your eye is irrelevant to your perception. When you are looking directly at the source of energy, whether it has reflected off of a surface, it is the same. So whether you're looking at the source of light or the light after it's reflected off of a surface, it actually could be absorbed by a surface and re-radiated as a completely different wavelength or frequency. But the photon is a photon. Once again, I remind you that what you are creating is a perception, and it can be accomplished in more than one way. In light of what we have just showed you, what do we have here? What you see now are three planes of light. The three primary colors of light are red, green, and blue. All illuminated images are comprised of a ratio of these three primary colors. You will see this shortly. Now, let's do that again a little more slowly while paying attention to the red, green, and blue text as it passes in front of the light plane. So we're going to do the three light planes, red, green, and blue text again. Watch as it passes through. You'll see that each color of text disappears or blends into the light plane. This is an important point to remind you that a red photon of light is a red photon of light. This will become more apparent later as we continue. The red, green, and blue text are identical colors as the three light planes and indistinguishable one from another, meaning the red text is indistinguishable from the red light plane. Now let's overlap these three primary colors and see what the results are. If we were to shift these light planes and actually have them cross over to combine red and green, blue and green, and red and blue, this would be the results. Now I added a fourth light plane to accommodate the mixing of red and blue since they are not adjacent in my illustration. These are the three secondary colors of light. So if you blend red and green, you get yellow. If you blend green and blue, you get cyan. If you blend blue with red, you get magenta. For some of you, this is old hat. I mean, this is information you've known for many years. For others, you may have just realized that the three secondary colors are the colors of your ink cartridges in your printer: magenta, yellow, and cyan. And of course you have black. And sometimes you have two black cartridges, photo black and regular black. But nonetheless, we're talking about color here. A little bit later, we will discuss the fact that light, when it comes to primary colors, is an additive process, meaning the more light you add, the brighter it gets. Whereas paint pigment, when you mix paint together, pigment, that's a subtractive process. So the three primary colors for light are a little bit different than they are for pigment or for paint. Magenta, as I said, is a mix of red and blue. Yellow is a mix of red and green. And cyan is a mix of green and blue. If you are new to color, Light is an additive process, whereas pigment or paint is a subtractive process. With light, all colors mixed together result in white. With pigment or paint, all the colors mixed together give you black. When you mix light, you are adding more light. You're adding more frequencies, more wavelengths. Hence, you have a brighter light. When you add pigment, since each pigment absorbs all the other colors except for its pigment and is therefore subtractive because it subtracts light and results in a darker result. So if you look at the colors up there, if you mix red and green together with light, you get yellow. Have you ever mixed red and green together with food coloring or paint? If you did, you get brown. Just the opposite. It goes darker. If you add red, green, and blue together, you're going to get black. Now, it may look gray because true black is hard to acquire with pigment. Nonetheless, light is an additive process and pigment is a subtractive. Now, let's look at these colors one at a time, beginning with magenta. Magenta, and if you look at the spectrum up there that begins with red, goes red, green, blue. But notice that they added red to the far right so you could show red blending with blue. If you've ever worked with any graphics on a computer, then you recognize this pop-up. Red is at both extremes instead of blue like I chose to do. Nonetheless, you see why they put red at both ends. This 8-bit color system, which we will be working with later. So this is 8-bit color that you're looking at right here. Now, the reason that I know that, and you probably know that, is that 8 bits numerically give you a value of 0 through 255. Now, if you don't even know what a bit is, it's a single bit is the smallest piece of information in a computer. It's either 0 or 1. If you were to work with a binary number system and you had 8 bits, in other words, you had a number that was all ones and zeros and it was 8 values long, in binary values converted to decimal, which is what you and I all know how to talk about as decimal. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, so on. So when I look there and I see 255 and 0, I know that this is a 8-bit color system, which means the value of red can be 0 through 255, 0, 1, 2, 3, 4, 5, all the way up to 255. Green can be 0 all the way up to 255, and blue can be 0 through 255. As you can see here, magenta is a maximum of 255 red and maximum of 255 blue and a minimum 0 of green. Yellow is a maximum of 255 red, a minimum of 0 blue, and a maximum of 255 green. So you look down there at the red, green, blue values. The reason that this is important, and by the way, cyan, we'll just throw that up real quick. Cyan, you can see, has no red. It's all blue and green. Now, the reason that is important for you to understand this, when you create your LED luminaire and you start adjusting the amount of red, green, and blue light to mix together to get the color that you want, you can use these charts right off your computer graphics applications. And if you wanted some particular color, you can pick the color in this spectrum and then look down below to see how much red, green, and blue you have to create that specific hue or color or tint, if you want to call it that. Now, working with the LED controls and the driver adjustments that you can purchase to control the LEDs, it's not real exact. But those drivers, which you will see that in a later video, they are 256 levels. They're 0 through 255. 0 counts as a level. The first level is 0 all the way up to 255. That is a total of 256 different levels. What about all of the other 16 million plus colors available from 8-bit color? Actually, there are 16,777,200 216 possible combinations of red, green, and blue when each one has 256 individually settable levels. So if you started with this chart right here and you set all three of those at 0, and then you increase red by 1, then 2, then 3, then 4, all the way up to 255, that's 256 levels, so to speak. But they're all some value of red. And then you can go and do that again for green with all the rest of them 0, and then do it for blue. Then you can go back and set red up to 1, and then bump green to 1, then 2, then 3, all up to 255. So you see, you have 256 times 256 times 256 possible combinations with these 256 levels of each of these three colors. And that works out to 16,777,216. Now, if you want to throw away the 0 levels, if you want to throw away black or white, that's fine. You're still going to end up with more than 16 million possible colors. Now, let's pick something besides the primary and secondary colors. Here we have mint green. First, we add a line between the green and the blue, which is cyan. So we throw a line in there, and we say that line represents perfect cyan, an equal distribution of green and blue. For your light source, you turned off the red, and then you bring up the green and blue to equal values. That's going to give you cyan. It's going to give you 256 or 255 levels of cyan. However, let's say you pick a color like I have here in the text, mint green. If you look at the little crosshairs, you see that it's more green than it is blue. It is to the left of the cyan line. If you look down below, you see that you actually do have some red. Now, this gets a little bit more complicated because it takes red, green, and blue to make white. And if we were to drop that crosshairs further down the chart there, then the red, green, and blue would equally decrease in value until all you had left were green and blue, but they would not be equal in value. You'd have more green than blue. Nonetheless, just to make this practical, because I got a little off course here, think of this in terms as, you want that particular color, you pick it, you see that's what you want, go down, look at the chart, and you're going to need, out of 255, you're going to need 29 blue, 226 green, in other words, mostly green, and then 157 blue. The point is, you have more green than blue. If you want to get really technical, you could subtract 29 from all three values, and what you would have left would be just green and blue. And that is actually what you want as far as the color goes, not the intensity. But this is just to give you an idea of when you mix the colors together, where they fit on this chart, and what those values mean down there for you trying to adjust your luminaire to get the color that you want. We're going to stop here. This presentation has arrived at the 30-minute mark. We don't like to make the videos any more than 20 to 30 minutes long because for two reasons. One is we don't want to make people sit for any length of time greater than what they're comfortable with, and we don't want to make them have to go back to an hour-and-a-half presentation and work their way through to try to get back to where they were at. So we try to break it up into smaller pieces. So thank you for watching part 1. Now you need to find part 2 in the playlist, or however you find it on your source of videos on YouTube, and watch part 1, An Introduction to Light and Energy, continued.